Hi, welcome to another edition of Mr. Weis Solves an Old AP Problem. Today we are working on problem 2 from 2009, AP Calculus BC, question number 5. This is one of these relatively frequent questions you're going to see where you're given some chart of values for some function, but you don't know the actual function, you just know some of the values. They usually give you some other information. In this case they're telling you that this function is twice differentiable on the real numbers, and they're giving you these values. Interestingly, these x values correspond to Fibonacci numbers. I wonder if that was on purpose or just something fun that the writers of the test did. In any event, the first problem is asking us, part A, is asking us to estimate f prime of 4. In other words, we would like the slope of the tangent line to f of x at 4, and we're going to estimate it using only these values here. Now, I think it's likely that they would accept a number of answers here. You have to show the work that you're going to do, but I think it's likely they would accept another answer, a number of answers here. I think the most obvious and probably best estimate for what f prime is, given the information we have, is to find the slope of the secant line that goes around from points around 4. Namely, we have x values for 3 and 5. So I think my answer is that f prime of 4 is approximately going to be f of 5 minus f of 3 over 5 minus 3. This is literally the slope of the secant line that passes through the points 3 comma f of 3 and 5 comma f of 5. By the mean value theorem, we actually know that somewhere between 3 and 5 there must be some place where the slope of the tangent line actually equals this number, at least one place by the mean value theorem. Perhaps 4 is that place. Perhaps not. That's why this is just an estimate. We don't know whether it's going to work or not. So here we go. My answer is therefore f of 5, which is negative 2, minus f of 3, which is 4, 4 over 5 minus 3, which is 2, which gives me negative 6 over 2, which is negative 3. And that's my final answer. Okay, here we are on part B of the 2009 AP Calculus BC exam, problem number 5, in which we're given the values of this function f of x over at certain x values. We're told that the second derivative of this function also exists. Part B asks us to compute the following very strange integral and to show the work that leads to our answer. I think the key thing about this problem and what it's trying to get is to try to get you to make sure that you understand the way definite integrals and indefinite integrals work, as far as how they work with dealing with minus signs and plus signs, how they work with constants. So for example, hopefully very quickly you realize that this is just the integral from 2 to 13 of 3 dx minus 5 times the integral from 2 to 13 of f prime of x dx. This is the linearity of what we call the linearity of the integral. Allows you to do this. So now as far as this one is concerned, you could, if you want, actually do this integral. I don't even bother. I realize that this is just a function, y equals 3. It's a constant function. I'm finding the area under the constant function from 2 to 13. So if this is 3, up at 3, and we're going from 2 up to 13, it is simply that area right there. And that area is 13 minus 2, which is 11 times 3. So this is 33 minus 5 times, now I use the fundamental theorem of calculus part 1. This equals any antiderivative of f prime from 13, plugged in 13 into that, and subtract 2 plugged into that. Any antiderivative of f prime, including f itself. So this is f of x from 13 to 2. We usually choose the antiderivative where the c is 0, but we're actually free to choose any antiderivative we want, including, in this case, the function f of x, which we don't know. So this ends up being 33 minus 5 times f of 13, which is 6, minus f of 2, which is 1. So this ends up being 33 minus 5 times 5 is 25, which ends up being, what's that, 8. And that's my final answer. Okay, here we are doing part C of the 2009 number 5 AP Calculus BC exam. We're dealing with this function f of x. We do not know the actual values, what this function actually is. We just know a couple of values, and we know that it's twice differentiable for all real numbers. Part C of this problem asks us to estimate the definite integral under f of x using left Riemann sums and the values given to us here. So that's what I'm going to do. I'm going to end up doing 1, 2, 3, 4 rectangles. 4 rectangles, and we're using it's the left Riemann sum, so I'm always using the left endpoint as the height of my rectangle. So here we go. This is not equal to, but it's approximate. So my first rectangle is going to have a width of 3 minus 2 and a height of f of 2. Plus, my second rectangle has a width of 5 minus 3 and a height of f of 3. My third rectangle has a width of 8 minus 5 and a height of f of 5. And my final rectangle has a width of 13 minus 8 and a height of f of 8. So putting this all together, it looks like I have a 1 times a 1 plus a 2 times f of 3 is 4 plus 8 minus 5 is 3. F of 5 is negative 2, plus 13 minus 8 is 5, and f of 8 is 3. So it looks like we have 1 plus 8 minus 6 plus 15. So let's see. So that's 9 minus 6 is 3, 3 plus 15 is 18. And that's my final answer. Okay, here we are on the final part of the 2009 number 5 AP Calculus BC exam. This one is a bit of a doozy. So again, we're working with this function. We know a couple of its values. We don't know much else about the function except that the second derivative always exists. In the final part of this, we're given some extra information. We're told that the derivative of f at 5 is actually equal to 3. So we also know f prime at 5. And we're also told that on the interval from 5 to 8, for sure, f double prime is concave down. Or sorry, f double prime is negative, which means f is concave down. Okay, what they want us to do is show two things. Show that f of 7 has to be less than or equal to 4, and show that f of 7 also has to be bigger than 4/3. So we're finding ranges on where f of 7 can be. Okay, so starting out with this one, here's what I'm going to do. I'm trying to figure out what's happening at 7 with f. 7 happens to be between 5 and 8, and we actually know a lot about the function between 5 and 8. In particular, I know a lot about what's going on specifically at 5. So I'm going to start by finding the tangent line to f at 5. So the tangent line to f of x at x equals 5 is given by the following thing, point slope form. So I have y minus its value at 5, so that is negative 2, equals the slope at 5, which is 3 times x minus 5. So when I clean this up a little bit, I think that we end up getting that y equals, let's see, so that's going to be 3x. I'm going to have minus 15, minus 2 more, so minus 17. Okay, so this is the tangent line to f at 5. So if I were making a graph of f, here we are at 5, and we've just figured out our tangent line looks something like this. Boop, there's our tangent line. It's got a positive slope, but there it is. Now, what do we know about this function? We know that this function is concave down. We know that this function is concave down on this interval. So what that means is that it must go kind of like this. It has to go like that. Which means that if I plug 7 into this, if I plug 7 into the tangent line instead, I'm going to get a value that is above f of 7. So f of 7 is less than the value I get when I plug 7 into the tangent line. That is, f of 7 is less than or equal to, plug 7 in here, and we get 3 times 7 minus 17, which is 21 minus 17, which is 4. And there we have it. So this is why f of 7 has to be less than or equal to 4. I'm using the concavity and the fact that I know that it's always concave down. Now we also want to show that f of 7 is bigger than 4/3. So for this, I'm going to do something slightly different. For this same kind of picture, I'm going to make the secant line that goes from 5 all the way up to 8. And if I make that secant line that goes from 5 up to 8, in this case, I can see that that secant line's value is always, if I plug 7 into the equation of the secant line, it will be smaller than what happens when I plug it into the actual curve. So let's find the secant line. The secant line for f of x at x equals 5 and 8. So I don't know, I'll take the point 5 to be my, I'll still use point slope form. So I'm going to have y minus negative 2 equals, we're going to have to figure out the slope, x minus 5. So the slope is f of 8 minus f of 5 over 8 minus 5. We calculated this already, I'm not sure. So f of 8 is 3, f of 5 is negative 2, so I have 3 minus negative 2 over 3. So I think I have 5/3. So that's what goes here. Again, simplifying all this up, I think we have y equals 5/3 x, let's see, minus 25/3 minus another 2. So we have minus 25/3 minus 6/3 is minus 31/3. Cool? And now, as discussed from before, the actual value of the function at 7 should be above the value of the function, the value of the secant line at 7. That is, f of 7 should be greater than or equal to 5/3 times 7 minus 31/3. And that's 35/3 minus 31/3, which is 4/3. And that completes that problem.